Okay, since so many of you are having a hard time with this, and some of you are having a hard time paying attention in class, I thought I'd record this video for everybody. And what I did was I shared this spreadsheet with you. This is just that world population data that we looked at in a little bit different way. And then what I did is I took, remember when we did the scatter plot for this? In fact, why don't I do this since I'm recording this video? Chart. And we're going to do a scatter plot as soon as this loads. Change it to a scatter plot. Here we go. So we're seeing something that looks kind of linear, but remember when we looked at the residual plot, there was some very large errors. So, and it didn't really look like a linear model would be the best model to use. And if you think about it, it is a population growth, which would be an exponential model. So what I did is I looked at that ladder of power sheet and I calculated all these values from the population. And you can click on the sheet to see how I did it, because I've shared this with you. And then what I did is I copied and pasted this into a StatCrunch sheet. And let's see, my StatCrunch sheet, is that here? Yes. So now what I can do is I can do a bunch of analyses here. I want to look at all the different combination pairs. And what's nice about using this in StatCrunch is it does a lot of the calculation for us, so that you don't have to worry about all that. So what I'm going to do is I'm going to do a stat regression simple linear. And I'm going to select the year since 1950 as my X variable. And just for the sake of to see what it looks like, here's to the first power. I'm going to ignore the hypothesis testing. I do want to have a graph residuals versus X values. I also want to graph a fitted line plot, and that'll give me the scatter plot with the regression line on it. It'll give me the residuals. It'll also calculate the least squares regression equation for me. So I'm going to compute this. And what am I looking at? I'm looking at, remember, here's a regression equation. Here's r squared expressed as a decimal. So if we want that as a percentage, we got to multiply that by 100. So 99% of the change in the world population can be explained by an increase in the number of years. However, and here's the scatter plot with a line. You can start to see how they're looking like there's a pattern there. I talked about that on the board. See how the line is above the actual data in the middle, and it's below it. And if we look at the residual plot, you see the line y equals 0. That's when there's the actual data is right on the regression equation. And we're seeing some pretty big errors in this residual, and we're seeing that curved pattern. So even though r squared is such a high number, we're looking at the residual plot, and this is necessarily going to be the best model to use. If we try picking years in between, well, was that 1960 and 1990, there was going to be some big errors in what the line's predicting. And then again, if we were trying to go out beyond, let's see, that'd be 2000. There'd be some errors going on there. We don't know what's happening. That's the case for extrapolation. Not looking too promising. So we have to straighten this data a little bit. So then let's compare the years since 1950 and the population squared. So I'm going to do stat, regression, simple linear regression. I'm going to select years since 1950. But now I'm going to do the population squared. I want to make sure it graphs a fitted line plot. I want to make sure it graphs residuals versus X values. Whoops, residuals versus X values and the fitted line plot. I'm hitting shift, not control. Let's see, residuals versus X values. Now let's compute this. Here's the regression equation. R squared is a little lower. Let's take a look at, there's the line. I'm still seeing some patterns going on, and I'm still seeing big errors. So that certainly wasn't the way to go. So we're going to discard that attempt. So stat, regression, pretty quick here, you guys are going to be able to do this. Simpler regression, I'm going to do years since 1950 as my X, and I'm going to do the square root of the population. And again, I want to have a fitted line, and I want to do residuals versus the X values. And a good, the R squared is right back up nice and high. There's my regression equation. The square root of the population is equal to that. And let's go to the next page. Look, see how graphing the square root of the population, it's not quite such a gap here between the line and the data. And then if we look at the residual plot, I'm seeing it certainly looks a little more random. I'm seeing a little bit of a pattern here. I mean, it's kind of low at first and kind of high at, if you remember, this is the residuals. This is graphing the errors. So it's better than before. Still, I'm going to try to do better. I'm going to try to do better. So now let's try the years since 1950 and the log. That might kind of make sense since it is an exponential growth kind of model. So I'm going to do stat, regression, simple linear regression, 1950. I'm going to try the log of the population. And again, make sure the fitted line is graphed, and then the residuals. Let's see what this looks like. So R squared still nice and high. And there's of course, here's my regression equation. And there's the plot. Still, I don't know. We'll have to see what the residuals look like. Same kind of error pattern, you know, kind of constant. So it's a potential, certainly better than squaring the population. Let's try some other options. The reciprocal, let's try that. So stat, regression, simple linear regression, years since 1950. The reciprocal square root of the population is what we're going to try. And again, fitted line. We want to take a look at that residual plot. Nope, not Q, residual plot. Let's compute it. R squared is a little lower than before. Let's see what the plot looks like. Kind of changed the direction, didn't it? And I'm back to seeing some patterns here. So I don't know. Yeah, so that certainly wasn't the way to go. This was what? This was the reciprocal square root. So not the way to go. One last choice in this ladder. Regression, simple linear regression. We'll do years since 1950 and the reciprocal of the population. We'll do the fitted line, residuals, compute. R squared is a little less, and that's looking like pattern. There's the QQ plot. I guess I must have selected the wrong one. Let's edit it. Here we go. Yeah, no, it was a residual plot, not the QQ plot. Let's check that out. So ooh, not good. So see, that pattern's back. But with that said, I am seeing a pattern, but look at those errors. I mean, those errors are within, those are incredibly small errors, right? What is that? That's tenths, hundredths, thousandths, 10,000ths, 100,000. So within 2 100,000ths. So even though I'm seeing a pattern, those are very small errors. This is the best one we've seen. So I'm going to go with this one. This is the regression equation that I think fits the data the best. R squared is still really high, and the residual plot shows very small errors. Even though there's a pattern, the errors are very small. So that's the regression model we're going to use to make predictions with this. So now, hopefully this helps you work through this. We'll try working through the light intensity problem and maybe the next problem with the StatCrunch tomorrow in class.